I'm going to be going through at a high level and then with a live demo, what is PyTeal, our Python library for smart contracts? How do you use it? How does it fit in? And what are some of the things you can do with it? So that's the focus of this talk. Real quick, by a show of hands, how many of you are developers? Okay, good. You guys are in the right place. Yeah, if you've already have seen PyTeal, I'm sure you're going to learn a few new things. And if you haven't, this is great for you as well. We're going to go from start to finish, and you'll kind of learn enough where you can just jump off and continue your own research and learning. Cool. So this is the outline for today. I'm going to go over what PyTeal is, how it fits in. We're going to talk about all of the building blocks of PyTeal. Then we're going to go into a live demo, some additional resources, and then I'll talk about upcoming PyTeal features and what things could look like in the future. So let's get into it. To start with, PyTeal is our library for writing smart contracts in Python. A lot of people ask, why Python? Why didn't you create your own fancy language on top of Teal? And the short answer is, a lot of people use Python. It's super approachable. It's very a flexible language, which allows us to do some of the interesting things that we do for PyTeal. And it has a ton of existing tools for developers. I'm talking IDEs, type checking, syntax highlighting. These are things, every developer probably has their own preferences. We don't want to force you to use something that is just specific for Teal and requires a whole bunch of additional onboarding. We're trying to make this as simple as possible. So that's one of the reasons why, or a few of the reasons why we chose Python. And I've got a graphic here to show you how Python or how PyTeal fits into the flow when you're developing smart contracts. I'll start by explaining this end over here. This is the Algorand blockchain. This is where we run the smart contracts. And to get to that step, you need to have Teal bytecode. This is binary code. Okay, it's binary code. You don't want to write this. This is just the compiled space minimal version. And before that, we have Teal source code. So you may have seen this before. This is our assembly-like language. It's very basic, but kind of difficult to create higher level programs just because it is very assembly-like. So PyTeal comes in at the very left over here. You can create what's called PyTeal expressions, and I'll explain more in a few slides. You can create these expressions in Python with the tools you're already familiar with, and then PyTeal will compile these into Teal source code for you, and then you can continue the workflow here, and then eventually have that code run on the chain. So this is kind of the context that we're talking about. Cool. So to start with, I talked about PyTeal expressions. So the way that this works is I like to say that you're writing Python code that produces Teal code. So things are going to look a little different. You're going to be using our PyTeal objects to create these expressions. And you're building up an abstract syntax tree or an AST that represents your program. And then you're going to be calling this compile Teal method right here. And that will do all the work necessary to convert that AST into the actual Teal source that we were talking about right here. And then you can continue the process to actually deploying that to the chain. So here's just some boilerplate, the import that you'll need, the compile Teal method that you'll need, and we will drill into all the building blocks of how you create that specific program right now. So to start, PyTeal is pretty simple. There are only two types. You've got unsigned 64-bit integers, and you have byte strings. So here's a few examples. You create them by wrapping them in int and byte objects, which are specific to PyTeal. So you can put integers in, wrap it in int, and then you'll get a PyTeal expression that represents that value. Same thing for bytes. You can pass in a string, a byte array. We even support base 16, 32, and 64. So you just pass those right in there, and now you have these constants that you can reference in your PyTeal program. We also have some functions for converting between types. So we have int to byte or I to B, and that will help you convert from integers to byte arrays, and B to I is the reverse of that, because you might have to do that for some specific things in your program. And so I will note these functions, you're using them to create your abstract syntax tree in PyTeal. So they're not executing immediately when you call them. What's happening is your program is building up the set of instructions that it will essentially do at runtime. So this is saying, I'm having a Teal program that will convert this integer to a byte array at runtime. It's not actually happening in the Python environment itself. Cool. So next up, we have some basic math and crypto that's exposed to you in PyTeal. The first of which is basic math. We overloaded most of the Python math operators. So you can do things like addition, multiplication, modulo, things like that that are necessary. Oops. We also have and or for Boolean expressions. You can just, we use 1 and 0 to represent Booleans, and you can use those to actually build up larger expressions. Byte strings also, we have some functions for those. We have concat, which concatenates 2 or multiple byte strings. And we have substring that lets you take a subsection of that byte string and pull it out. We also have the length, or len for length, that lets you get the length of a byte string there. And then just to show you, this isn't all of our crypto utilities, but we do have a few specifically for hashes. You can pass in a byte string here. PyTeal, or sorry, the AVM will hash that for you, and then you can get the result back. So it isn't just basic manipulation. We also support kind of some more in-depth crypto on top of that too. All right. So I've shown you kind of the basic types, how you can do some computations. But the interesting thing is, what information do you have access to in these programs? So this is where transaction fields come in. If you don't already know, smart contracts have to be invoked by a specific application called transaction type. And this transaction, you can kind of set fields on it to describe the input to your program. So some of these inputs are like the sender of the current transaction. There is an array of accounts that are associated with the transaction that you can access. So you can get the length of that array. And you can also just use indexing to actually look at the elements there. Same thing here for application args. This is specifically meant for arguments to your application. And so you can use these as you see fit and extract what you need, do your computation, and then kind of take the actions that you need. You can also get the index that your transaction is in an atomic group. If you don't already know, Algorand transactions are special in that they can be part of larger groups of transactions, up to 16 at once. And the way this works is if any of those transactions fail in that group, the whole thing gets thrown away. So it gives you nice properties that you can essentially tie 2 or more actions together and be confident that if it succeeds, all of those actions have succeeded. And so you can also actually look at all the properties from the transactions at any index in this group. So we've got here GTXN0 will get you the sender of the first transaction in the group. You can also pass in kind of more complicated expressions here. Like this line right here, what we're doing is we're actually finding, looking up the transaction immediately before us in the group. That's what the -1 is, finding the sender there, looking at the second account that was passed in here. And you can do that for every single field that's accessible from the current transaction too. And lastly, there's a few global fields down here. You can look up the size of the group, what round number is currently being processed right now, and also the latest timestamp in Unix formats, like seconds since 1970, and use that as you see fit in your application. Great. So that was kind of explaining how to get information into the contract. Now I'll kind of explain a few ways you can output things from the contract. One of them is pretty simple. It's just calling a log function. And what this does is it takes in a byte string and it announces it publicly on the chain. So this can be very useful for debugging. It's essentially the equivalent of a print statement. You can print out whatever information you want here. And you can also just announce that certain events happened and then listen for them other places. All right. And so a big part of applications is state. There are two types of persistent state in the AVM. The first one is global. And so you get one context, one key value store per app that's global. And you can do interesting things like set a key value. So this first line, app.global_put, we're setting the key status to the value active. And then we can read that value with app.global_get. So we just pass in the key that we want to read. And that will look up the value at that point in time and return it to us. And then we can also look at, we can also delete keys by calling app.global_del, and that will delete a certain key. Yes? Yes, so as I was saying before, these look like commands that are executing as soon as you call them, but they're not doing that. It's really just building up a set of instructions, and nothing happens until you compile and until you submit this to the chain and then run commands on it there. Yeah, so this is just a, hopefully an intuitive way for you to build up your app, but knowing that you're writing code that writes code, essentially. So it is a kind of a little bit of a difficult paradigm to get used to. Yeah. Okay, there's also a second type of persistent state. This one's called local. And this solves the problem of, if you're making an app that stores one integer per user, you only have so much global state. And eventually, you won't be able to support an infinite number of users. And so this is where local state comes in. Instead of storing everything globally, you can store key values per account that is opted in. So this will let you scale to as many accounts as possible. And this works very much in the same way as global state. You've got local put, local get, local del. The only difference is we have an additional parameter at the front, and this tells us which account that we're dealing with. So this first example, app.localPut transaction.sender, that is putting a key in the sender's local state. We can also use any of the other accounts in the accounts array and put read, write, delete keys from those accounts as well. So this is the second type of persistent state. Okay. And now I'm gonna go through a few slides about control flow, which is probably the one of the most interesting parts, because you actually have to be able to build up these logical steps in order to do different things based on different conditions or based on different inputs to your app. So the first part of this, we have approve and reject. These are special commands that you need to use in order to tell the chain, yes, my program was successful, and I want to commit any changes that have happened during the runtime, or no, this program was not successful for some reason. Maybe there was a bad input, or maybe someone tried to perform an action that isn't supported. You would reject in that case. And if you reject, any state changes that you have made temporarily will get rolled back, and there'll be no record that this program ever executed on chain. And so as soon as you call one of these methods, your program will immediately stop. And if it's approved, it'll get committed to the chain. If you reject, then it'll get thrown out. All right. And so you probably want to use multiple expressions at once. Otherwise, your program wouldn't be very useful. And so we have this sequence expression that lets you combine as many essentially lines of code as you need in PyTeal. And so this example right here, this is a program that essentially just counts how many times it was called. So what happens is we're setting the key count to the value that count currently holds +1, and then it always approves. And this is using the fact that app.global-get will return 0 if you essentially try to look up a key that doesn't exist yet. We just return a default value of 0. So that's how that works. All right. You cannot pick a different default. No, it's always going to be 0. But you can. I didn't show it here, but you can ask if a key exists, and then have special logic in there to handle that. Okay. This slide is all about branching and handling different conditions. So we have if, then, else, and else if, which let you do that. If right here at the top, this is branching on the condition my count equals 100. And if that's the case, the then block will get executed. And so I will remember who sent the transaction that was the 100th caller of this app. Otherwise, I'm remembering that the sender was not the 100th caller. And this key would get overridden every single time the program runs and the count isn't 100. And then in all cases, after that executes, I'm still incrementing the count like I was before, and then approving in all cases. Does this make sense? Okay, good. Great. And very often you'll want to actually, instead of doing essentially just a bunch of if-elses, you'll want to branch based on a bunch of different possibilities. And so this is, we have a statement called cond that's very similar to a switch statement in other languages. You essentially put in a condition as the first part. And if that's true, then your predicate will get executed over here. And if all of them are false, then an error will happen and your program will terminate unsuccessfully. So this guarantees that one of these cases will be true and will execute. Otherwise, the program will fail. All right. And I will add that this is a piece of code that's very common to see in PyTeal programs, because you essentially want something to happen on create, and that's that condition there is how you check that. You want to handle updates to your application in a certain way, deletion requests to your application in a certain way, and the same thing for these other ones. So this is a very common thing to do in PyTeal. All right. And so the last control flow slide I have is about loops. So we do support for and while loops in PyTeal. They are very useful to use with what we call a scratch variable. And this, instead of representing a constant, this represents a variable that you can read and write to as many times as you want in your program. So what's happening here is I created a scratch variable, and I'm saying that it will hold a uint64, and this just helps with type checking at compile time. And then I'm creating a for loop. I'm setting the initial value to 0. I'm going until it's less than 16. I think this is a typo. This should actually say i.load is less than 16. And then we're essentially storing the value of I plus 1. So this is the step of the for loop that actually increments that. And every time it runs, whatever you pass into the do block will execute. So this is happening to essentially iterate 16 times and set a key index plus whatever encoding of the integer we're currently on, and then just setting the value to 1. So you can initialize a lot of state that way. Yes?
The scratch block you chose for it less than 16, or is it an error? You can't run it.
This will be an error, yeah. It'll essentially say there's no operator overloaded for the scratch variable type, yeah. So you would catch that at compile time for sure. Okay, great. Another question, yeah?
What's the purpose of the validator got the right system time, or is set to the right?
That's a good question. I'm not sure. Yeah, we can talk about that after maybe, and I can help you with that. That is a consensus question. Yeah, any more questions right now? Okay. All right, and you can use this same construct for while loops as well. I just don't have an example of that. But essentially, instead of 3 arguments, there's just 1, and that's the condition. All right. Another really interesting tool is subroutines in PyTeal. Subroutines are essentially functions. They're pieces of code that you can put inside a Python function. You add the subroutine decorator like that. And you can also declare the return type, which is helpful for type checking. And then you can call the subroutine from later on in your program, just like a normal Python function. It looks the exact same. But this, what's actually happening at compile time is this code gets stored once. And every time you invoke it, we essentially go to that subroutine in the AVM, invoke it, and then come back. So if you're calling a function many times, this is a good way to reduce the amount of duplicate code that you have and shrink your program size down. And so I will add recursion is allowed in subroutines, which is a really powerful feature as well. So here I've got another implementation of is even, except it uses recursion. I've got 2 base cases. If I is 0, then I know that's even. If I is 1, I know that's odd. And then otherwise, I just subtract 2 from I, and I recursively call the function again. So this is allowed, perfectly acceptable. You can also do mutual recursion between 2 or more functions if you want. Yeah. Is there a question over here?
Yeah. What happens if you get too many calls in the stack?
So there's no limit to the amount of recursion that can happen, but there is a limit to your total opcode cost. I think it's 700 per application call. So, you're not going to be able to do recursion more than 700 times because you'll just hit the opcode limit anyway. Okay. Cool. All right. And so the last kind of building block that I wanted to show was inner transactions. And as of AVM 1.0, applications can create and execute individual transactions. These are called inner transactions. And the way this works is every single application has an escrow account that they control. And you can use this expression to find the escrow account of the current application that's running. And what you can do with that is send transactions from this escrow account that your app totally has control over. And right here, what this is doing is we're using the inner transaction builder. We call begin. We call set fields as many times as we want. And then we call submit. And once you call submit, immediately that transaction will execute. If it's successful, your program will keep going. If it fails for any reason, maybe the escrow account doesn't have enough funds. Maybe you're doing something that just isn't allowed. You're trying to, I don't know, send something with an amount that doesn't make sense. This is going to fail submission, and your entire app will actually fail on top of that. So every time you submit, you'll only continue if that submission was successful. So this specific example, we're creating a payment transaction type. We're saying the receiver is the sender of the current application call transaction, then invoke the application, and we're saying the amount is 1 algo. This is measured in micro algos, so 1 million equals 1 algo. Yes? I'm sorry, I couldn't hear. Good point. Yeah, so he asked if reject happens later on, what will happen to this inner transaction? That is a really good question. So every time you call submit, that inner transaction is executed. But if your app rejects for any reason later on, the entire kind of list of inner transactions is rolled back. So there's no record of those happening if you decide after the fact that your app will reject. Or maybe you submit 2 inner transactions, the first one succeeds, the second one fails, the entire thing gets rolled back anyway. Yeah. Cool. And I've got another example of an inner transaction. This one's a little more interesting. What we're doing is we're actually creating an asset inside this app. So these are the kind of parameters that you need to do that. It's an asset config type transaction. I'm calling it Decipher coin. I'm giving it kind of a unit name, a URL. I'm saying there are 6 decimals. This is the total amount of tokens that I'm creating. And I'm saying the current application address is going to be the manager. So the app is creating an asset that it has control over. I'm calling submit right here. So this executes that transaction. And at the very bottom, I'm remembering the ID of the asset that was just created here. So you can use the inner transaction object to inspect the transaction that was most recently submitted. And created asset ID is just one of the fields that is accessible to me there. And I'm just remembering it using app.global put the ID of that generated asset. Cool. Are there any more questions right now? Yes. Right. Yeah. So because when you create an application, the ID is unknown, the address is also unknown because this escrow account is actually derived from that application ID. So there's no way to know at creation. But what's a common method, and I'll show this in the demo, is you create your application and then you fund the account and like set it up to do the right thing. So create returns the application ID, and then you can use goal or one of our SDKs to derive the address from that ID. Yes. Okay. Great. So yeah, with that, it's time for the demo. And so this demo is adapted from some code we already have. It's an auction demo. It lives in this GitHub repo here that you can check out. And we also have a great article on the developer portal that goes kind of more in depth into that if you want to look at that after the talk too. Okay. Yeah. All right, let me make sure my hotspot is on. Cool. All right. So I will just show off very quickly. Can't see that. That's not good. Let's see. Need to mirror this screen. All right, cool. So this is the GitHub repo I was talking about. Feel free to check this out to actually look through the code. There's a lot of kind of documentation in line with the code. So that's very useful if you want to get started. And this is that article that I was talking about on the dev portal. The basic premise is we have a user called Alice. She creates an NFT. And another user called Bob is going to help her set up an auction for this NFT. And then Carla is going to come bid on that NFT and then win the auction and actually have that NFT transferred to her account. So that is our premise. I will start by showing you the contract in PyTeal and explaining some of the parts. Then I will show you essentially what the code looks like using the Python SDK to actually create the right transactions and invoke the app in the right way. And then lastly, I've got the live demo that actually does all of this on testnet, and we'll watch it in real time. And fingers crossed, there'll be no issues there. Okay, so probably the best thing to do with this is to start at the very bottom. And I've got a condition here that'll run when I invoke this contracts.py file. And what it does is we're calling compile Teal to actually convert the PyTeal AST into the Teal source code, and then we can use that to eventually deploy it to the Algorand blockchain. And so what we're putting into here is the output of this approval program function, and this defines the bulk of the program that I'm going to be using. And I will again kind of start at the bottom and then work my way up. So this is the thing that's being returned. We have one big condition that branches based on a few different events. And so if my application ID is 0, this is how we distinguish a creation transaction versus one that's calling an existing app. On create will get called, and I'll show you that in a minute. if we have onComplete equals no op, which is just a normal application call, we'll go to onCall. If our onCompletion value is delete application, we've got a special handler for that. Otherwise, if any of these other things happen, they're not supported by this app, so we just reject. And also, if none of these conditions happened, we'll reject with an error because none of our conditions were met, so we don't do anything. Okay, great. So I'll go to onCreate first, and I'll start a little bit towards the top. We define a bunch of names for keys that this application is going to use in global state. And we'll scroll down to onCreate. We're just creating a sequence here that initializes all of the global keys to the values that we want on creation. So let's see here. We're setting essentially the seller to be the first value that's passed into application args. We're setting the ID of the NFT that's being auctioned as the second application args, and we're converting it from an encoded uint64 byte, or sorry, byte array that represents a uint64, and we're actually decoding that into a real integer using b2i. And then we set kind of the remainder of the keys we need here, the start time, the end time, etc., other parameters. And then lastly, we've got an assert condition here. And what this does is it verifies that this condition is true. Otherwise, it will reject the contract. And what it does is we just want to make sure that the start time has not already happened. And we want to make sure that the start time is less than the end time. And I've also got a message in here asking, like, should we impose a maximum auction length? You probably don't want an auction that lasts hundreds of years because that's not very useful. And yeah, probably a good idea, but this demo doesn't have it. Next part, we've got this setup stage. And this is kind of what I was explaining before. We don't yet know the escrow account when this onCreate is being ran. But the idea is we create the application, and then we call setup. After we fund the escrow account, we use this to essentially opt the escrow account into the NFT that's being auctioned, and then we send it the NFT. So it's been funded, it has the NFT, and it's ready to accept bids. And that's what this inner transaction is doing here. We are opting into the NFT, and I'm setting the receiver equal to the sender. And so that's how we encode and opt in Algorand. All right. And so on bid, this is what happens when someone tries to place a bid in this auction. Let's see. So first we have a big assert statement with a lot of conditions here. We want to make sure the auction has been set up, and this is how we check that. We want to make sure it's been started. So I'm getting the start time from global state. I'm making sure it's less than or equal to the latest time step from the previous block. And I also want to make sure the auction hasn't ended yet. So a similar thing with the end time. And then I have a few checks to make sure that a bid is actually being sent to the escrow address. So the way this app works is you need to call it in an atomic group, and the transaction immediately before the application call must be a payment to the application escrow account that has the amount of that bid. So we're making sure that there's a payment immediately before it. This on bid transaction index, yep, it's just group index -1. We're making sure that the sender of the payment is the same as the application call sender. And we're making sure that the receiver of the bid is the escrow account of the current application. And we're also making sure that the amount is greater than the minimum transaction fee. Because if you lose the bid, what happens is, and I'll show this in a minute, we will refund that bid to your account. And we can't do that unless you bid an amount that will cover the transaction fees for sending it back. So that's another constraint we have there. All right, so that's just our giant assert statement. And then here we have a condition to check if the bid amount is greater than the current leading bid plus the minimum bid increment. This stops people from essentially, if the price is 1 algo, doing 1.00000 algos, because that's not very constructive. You can set a minimum increment for bids. And then if this is true, then we have a bid that's actually valid. So we can kind of go inside here. We want to make sure if there is an account that was the previous bidder, we're going to repay that bidder. And I'll show you that in a second in this subroutine. Otherwise, we're just going to essentially set the appropriate values in global state to remember what the current lead bid is, who placed that bid, and we're also just also recording the number of bids for fun. And then we'll approve, and this transaction will stop executing. Otherwise, we'll reject because the bid didn't pass all of the constraints we had. And repay previous bid leader, let's just take a look at that, is essentially just creating an inner transaction to send the amount to the previous lead bidder minus the transaction fee. So we can actually do that without draining the escrow accounts algos. Okay. So that was how to create a bid. I'm not going to go through claiming your NFC at the end, but the code is here on GitHub if you want to check that out, and it's pretty similar. Deals with inner transactions, making sure the auction is finished, and things like that. What I'm actually going to do is run the auction now, because we're kind of short on time, and then I'll show you kind of a few key things, and then bring it back to the slides to wrap up. Okay, so I've got my terminal here. I've got everything set up for this to run on testnet, so I'm just going to execute example.py. And when I do that, my account that I'm watching here on Algo Explorer will see some transactions appear here that's actually conducting this auction. So I will run this. We're generating some temporary accounts to actually be the key players, Alice, Bob, Carla, and they will create the auction and bid on it. So here are the accounts that we've generated. We're now having Alice create just an example NFT for this auction. So her balance is 0 represents algos. She's got a little under 2 algos, and the NFT ID 482, etc. She has value 1. So Bob is now creating this auction. We have an ID for the auction, and we have an escrow account address for that auction. So Alice is then responsible for sending the NFT to that auction, setting it up. And we can see she did that here by looking at her balance and the escrow account balance. The NFT ID is 1. And now Carla is going to bid on that auction. So she starts with 2 algos. She places a 1 algo bid. And she also opts into that NFT so she can receive it if she wins. She's the only one who bids, so she will win, spoilers. But we just have to wait for the auction to finish in case anyone else wants to bid. And now Alice is closing the auction and claiming the funds that she received for that NFT. So at the very end, the auction account holds nothing. It was completely drained. Alice contains the bid amount, but she loses the NFT. And then Carla loses the bid amount, but she gains that NFT, and you can see that in her balance right there. Yeah, so that is the demo. We can head over to Algo Explorer to see kind of the new transactions that happened here. I think this first one is Alice. And you can kind of dig into this as much as you want and see the individual transactions which represent the actual things occurring. This is the asset, this is the dummy asset that we created. That was the NFT that got auctioned off. So you can kind of see it transfer through a bunch of different accounts here. All right. I will just lastly close this and show you very briefly what the Python SDK code looks like to interact with that auction. And it's a bunch of well-documented code here that essentially creates transactions in certain ways using the PyTeal contract, encodes arguments in the right way. I won't go into detail about this, but I encourage you to check it out if you want to see kind of a full end-to-end example about how to kind of create a complicated app like this. So yeah, that is it for the demo. Could we go back to the slides? Great. I want to finish up with first just giving you kind of some resources for learning more about PyTeal. We've got the GitHub page, the docs where you can read about all the different expression types. You can check out the library on PyPy to download it. And you can also ask questions in the PyTeal channel of the Algorand Discord server. And if you want to join that and you aren't in it already, here's a link for that too. Okay, and then the last slide is about kind of the future of PyTeal and what that could look like. Some of the things that are kind of in the backlog are supporting contract-to-contract calls. So this will happen once the AVM is updated to support that feature, because right now intertransactions are limited. You can't essentially have an intertransaction that calls another application because that's just a limitation right now, but we're looking to lift that soon. And PyTeal will be modified to support that. We're also going to be adding Arc4 ABI support. If you don't know about the ABI, it describes essentially a standard way that contracts should behave, how their arguments should be encoded, what their methods should look like. And this will make its way into PyTeal as well, and hopefully give you a more unified experience for that. And lastly, this is kind of a further out goal for sure. Right now, PyTeal, you have to build up the specific expression for PyTeal. But the goal is for one day we to have another box right here where you can literally just write normal Python code that describes a program. And we will analyze that code using kind of the Python AST libraries that already exist and transform that into, from a Python program into a PyTeal program, and then continue the pipeline over here to hopefully make it even easier to write these programs.